Hello. Okay. Good afternoon. So last day we have discussed geometric representation of signals. To do that, we have taken capital M number of transmitted message signals and capital N number of orthonormal basis function. And before that, we have discussed what is orthonormal, what is orthogonal. That is, what are the conditions of orthonormal and orthogonal basis function that we have discussed already. So today we will not go into that portion orthogonal, orthonormal conditions. Okay, one second. And I told that XIT, which is a signal which is going to be transmitted. That means it is XIT, you can say it as modulated signal in which message portion and carrier portion is there. Okay, this thing we have explained using this block where some these are the message points, okay, and multiplied by some carrier signal. Carrier signal is nothing but some basis function, okay. multiply multiply and add all, okay. So finally we will get a signal denoted by XIT, which is nothing but a summation of this product of these two. So now this signal is the modulated signal which is transmitted from the transmitter side. In this case, very clearly try to understand that 1, 2, up to capital N, these are nothing but basis function, and this basis function is denoted by small j. Okay, very clearly understand these basis functions are denoted by small j, and capital M denotes message points, which is nothing but denoted by I, small I. So I is varying in between 1, 2 up to capital M. For an example, suppose I am taking any BPSK signal where message point is 2. Two message points from the constellation diagram, we can say this is one message point, this is the origin, this is another message point. So two message points are there, but one basis function was there. That is why for BPSK, phi 1t, phi 1t, but two different message points, root of EB minus root of EB. Two message points, but basis function is only one. That means for the case of BPSK, capital M is 2, but capital N is 1. That's the thing I have discussed here. For by taking the example of BPSK and BASK or ASK. These things already have discussed. So this thing we have transmitted. Okay, just I'm trying to recap of the previous discussions. And transmitted signal, and this is the received signal. So received signal is nothing but the transmitted signal multiplied by some locally generated carrier. Then the output of the product modulator is passing through some integrator. Okay, that mathematical expressions we have written here. And we will get xi1 up to xin. This signal was only transmitted. You see, xi1, xi2, xin like this. And already I told that these two things together known as correlation receiver or correlator. Okay, so up to this we have discussed. Again, I told just a little bit. Today, okay, continuation of the previous discussion. Today, what you see? Just you see xi1 up to xin. That I have written here. xi1, xi2 up to xin. All these are together. You can denote it by xi some bar, xi bar. This xi bar is nothing but signal space, like a vector space in which different number of vectors point are there. Similarly, here it is signal space where different signals are there. Okay, this signal space is known as Euclidean space. Euclidean space, the terminology, Euclidean space. Example, xi1. So xi1 or xi1, whatever the thing is, it is your either this or this. For BPSK, I told xi1 maybe this or this. For ASK or BASK, you know. Okay. Now, what about the energy of ith signal? What about the energy of ith signal? Try to recall the previous discussions of suppose any digital modulation technique, like suppose BPSK. So if this is the origin, this is one point root of EB. Suppose this is another point root of minus root of EB. So what is the distance between these two? That distance is nothing but will give the information about the energy. I told it. That means what is the energy of this message point? That is nothing but the distance from the origin. Is nothing but the energy of this message point. Distance from the origin of this message point is nothing but the energy of this message point. Okay. So that is why you have to find out ith signal. What about the signal? Ith signal energy. That means distance will give the energy of the signal from the origin. Distance from the origin will give the energy of the signal, as well as you can say that energy means can say that is the distance from the origin of that particular message point. That's all. So how to calculate it? Just very simple thing. Energy calculation. Energy of the ith message point denoted by E suffix small I, integration of 0 to t. That is 1 bit duration or 1 symbol duration. It depends on the what kind of modulation technique you are going to use. Xi square t, this one. Now what about this xi square? From the last page only, I'm writing this expression. Xi t means summation of product of these two. Similarly here also, because the square is there, so two times we have written the same thing. By changing the j, here it is, we are using k instead of by changing the variable of the summation j and k. J number of basis function, k number of basis functions. Multiply these two and integration. We will get okay the energy. Now just rearranging this one, summation you are taking out, x and x this term we are taking out, integration 0 to t, and these two terms we have written here. From the definition of orthogonal, we can say that if j and k are equal, then this integration will give you 1. That is the definition of orthogonality or the condition of orthogonality. So if now this thing is 1, if j equals to k, so the whole in this all places of j and k, we can write down x of ij, x of ij instead of k. So what we get? Finally, what we are getting? We are getting x of ij square, and these two things are nothing but summation of j equals to 1 to n. So now we have this one. Now just to separate out this term, xi, j value varies. I1, xi1, xi2, xi3, xi4 like this, xi capital N square, adding all. Okay, this is denoted by this one, which is nothing but squared length of signal vector. Xi bar means what actually? See, xi bar means this one, which is nothing but, that means it's a vector, it's a signal space in which this and these signals are there. That means that thing only we are writing here. Mod of square is nothing but xi mod of square is nothing but the summation of all. That means this is nothing but the energy of the ith message point as well as distance from the origin. Distance from the origin or energy of the ith message point or ith signal. This is how we have to calculate any message point energy from the origin or distance from the origin. Energy is nothing but the distance on the constellation diagram. Okay, on the constellation diagram or signal space diagram or Euclidean diagram. Euclidean diagram, another name, Euclidean space or Euclidean diagram. Okay, so this is how we can calculate the energy and distance, energy or distance of any signal, of any message point from the origin. Okay, so up to this is the signal space representation of or geometrical representation of signal. Okay, that is up to this we have discussed today. After that, come to the next video where we are going to discuss some new topic. And interesting, definitely it's interesting, uh, but it's very rarely coming in the exam. But even though you should follow, okay, because it's in your syllabus. That's all. Once again, okay. Now new term is that Gram-schmidt orthogonalization procedure. What is that? In short, GSOP, GSOP, which is used, I have written the line, which is used to find out the number of orthonormal basis functions. How many basis functions will be there? Okay, that means what will be the value of capital N for given capital M? What will be the value of capital N for given number of signals? Okay, we will solve one numerical based on this. Then it will be much more clear to you. So the theory is that GSOP is a procedure by which you can calculate how many number of basis functions are required to represent m number of message points and what are those basis functions. Okay, so we will see the steps how to get all these things. Okay, for some example that I have set here, we know these things that binary signaling means two message points. M array signaling means M number of message points. Okay. And phi 1t, phi 2t, phi 3t like this, phi nt. So how many number of basis functions are required to represent n signals? That is the case. And to do that, we have to use GSOP, Gram-schmidt orthogonalization procedure. Now, what is the procedure? How to calculate? How to get all these things? See, first thing is that what you have to calculate step by step. First thing is that the first basis function. What will be the first basis function? There is some formula by which you can calculate the first basis function. And the formula is this one. It's very simple. Phi 1t, the first basis function, 1 xit given message or given signal divided by root of E1. So root E1 is what? Energy of the X1, X1t. To calculate this, just use this one, this formula. Whatever the value you are getting, put it here. You will get phi 1t. Very simple. So in that way, phi 1t you are getting. So what about phi 2t? Definitely not that phi 2t x2t divided by root of E2. Not like that. For the first basis function, this is the process. But for the next basis functions, process is different. What is the process? Now see, for defining other basis function, very important, for defining other basis function, a new intermediate function is introduced. A new intermediate function is introduced. What is that intermediate function? So very simply, very clearly try to understand. It's not a tough one, but it's a lengthy one. It's not a tough one, it's a lengthy. And you have to remember some process, some steps. So, and we will solve just now, we will solve one numerical. So it will be much more clear to you. So, what is the intermediate function? That is denoted by GIT equals to XIT minus summation of XIJ phi JT. Where XIJ, you see, XIJ is there, there is no T. So XIJ, it's something different. It's not a function of time. Xij is denoted by this one, integration xi and pi I. That is actually xij. Okay. Now we have this one. Okay. So what we are doing for the first basis function, this is a formula. But for the other basis function, there are some steps. First step is to calculate this one. Next step is to calculate this one. Okay. Then from GI, just now we got the value of GI here. This is this GI. From GI, you put GI here. The new basis function will be phi IT GI and root of integration of 0 to t GI square t dt. That is phi IT. Where this I will be your will starts from 2, 3 to n. One is missing here because already the first basis function we got. That is why I starts from, for this equation. Remember, for this equation, I will start from 2, not from 1. Okay, not from 1. Here I have mentioned two things very clearly. That is what is I and what is J. J means I told up to n. I means I told denoted by capital N. Okay, number of message points, number of basis functions. And the relation between n and m is that, this one. Never, never n more will be greater than m. That will never be possible. Okay. So that is what? That is a simple thing is that we have steps, two steps actually. First step is that we have to calculate this one, in which this is unknown. To calculate this one, we have to use this expression. After that, we have to calculate phi it from the GI. That's it. And phi 1 already have calculated this one. So, so this will start from phi 2t. That is why here 2 up to n. This is the simple step how you are calculating basis functions and how many number of basis function will be there for m number of message signals. Now, see this one. Using Gram-schmidt orthogonalization procedure, the numerical is find the orthogonal basis function for the set of given signals. That is, some signal is given here. So you have to find out the basis functions, how many basis functions will be there, and how it looks like. What are those basis functions? Okay, that is the case. Once again. So today we will calculate the first basis function. Okay. In the next video, we will discuss the remaining basis function. So very simple. Numerical is this, where x1, x2, x3, x4, these are the message signals are given. Okay, all these having amplitude 1, 0 to t by 3, 0 to 2t by 3, t by 3 up to t, 0 to capital T. Okay, after that, one thing you see in the given signal that addition of these two will give you this one. Is it? How? Very simple. X1, its amplitude is in the range of 0 to t by 3. X3, it's having amplitude in the range of t by 3 to t. If you're adding these two things, that means 0 to t by 3 and t by 3 to t, we will have one amplitude. So if you're adding these two things, we will get this one. That means we can say that the given message signals are not independent because one signal depends on other two signals. These signals depends on these two signals. So these message points are not independent message points. Are not independent message points. Some observation. Whatever the numerical given in the exam, first by looking at the numerical, you have to get some idea what kind of numerical it is. I have given you in assignment or somewhere I have given one numerical based on QPSK and delta modulator. Don't get confused in that because both are interlinked. After passing any signal through delta modulator, we will get something, some bit stream that will be passed through some process known as modulation. That modulation may be QPSK, maybe BPSK, maybe whatever it is. So all of things are interlinked. So you have to understand in that way. So whatever some numerical is given to you, so you have to understand the physical meaning of that. Whatever. So given thing is that given signals is signals are these. So m is 4 number of message points or signals. N that you have to find out how many basis functions are there and what are the orthogonal basis functions, and this condition we know. Okay. So what about the first basis function? First basis function, that is E1, is your 0 to this one, t by 3 x1 square dt. Just input the integration because this value is 1. Okay, now you perform the integration process, you will get this one. Okay, I'm not doing all the integrations. Okay, you will get this one. So what about this 5 1t x1 divided by square root of e1? So x1 is this something we are least bother about what is there actually inside the x1. Okay, and root of energy. What is that energy? Okay, root of t by 3. So just rearranging this, you will get this one, root of 3 by t x1. Okay, in the range of what about the value of this t 0 to t by 3, 0 to t by 3. So phi 1t is nothing but a signal which is having amplitude root of 3 by t in the range of 0 to t by 3. This is your phi 1. That is the first basis function. That is the first basis function. So that is the process how we are calculating the first basis function. Okay. To calculate the first basis function, first you calculate the energy of the first signal, put that energy here, and you'll get something here. Definitely mention the range of small t and just write down, draw this one about for what is I1 t. Remaining basis functions in the next video we are going to discuss. Okay. This video now I'm going to stop.